Okay, so here we are. I've finished drawing the diagram as well as putting the values. So I hope you can see this binary tree here. And let me just quickly explain what is going on here. So we have this binary tree. Every vertex basically has two children, as we have seen before. Each vertex holds a value, okay, and that is a key value, right? But now here's the thing: even for a tree, as I said, you're going to implement it using arrays. So every vertex has an index; it has a name of its own, right? So the top vertex has this index 1, if you see, right? Then index 2, index 3, index 4, index 5, 6, 7, up to 15. There are 15 vertices, they have their own names, 1 to 15, right? But now the ordering is different. The ordering is decided by the linking that we give. What is previous, what is next, what is child, what is parent, things like that, right? So this is going to be a different object from the array. This is not an array, this is a binary tree. All right, so we have these down arrows and up arrows which indicate what are children and what are parents and all those things. So now let's try and write down what these things are going to be. Okay, so how many pointers do we have? So I have written here on the left side, you can see binary tree, t dot key values I've already written down. Okay, so 23, 23, vertex 1 is 23, 23, then 5, right? Then you have 12, then 89, then 8, then 24, 5, 37, 56, and so on. Okay, so you have those values written down. The index is obvious once again, as I said, right? When you vary from left to right, the index increases. So index 1, index 2, index 3, index 4, index 5, and so on. Okay, how many pointers do you need? For every vertex, there is a child. There are two children, left and right, right? So t dot left will fill it later on, and t dot right, right? There are two children, and every vertex has a parent. So t dot parent. Is that okay? So now let me just align them. So t dot left, t dot right, and parent. We have all of those. Okay. These are the arrows. These are the pointers of the arrows that you have. And once you have that, it's complete, right? This is enough. So this will be the complete description of the linked list, binary tree as a linked list. I hope this is clear to you. These are all the things that we require for completely describing this linked list. All the key values and all the pointers. Pointers are of three kinds. They're either left child, there are either right child pointers or parent pointers. But that's it. Okay, that's all you have. So now let's fill in t dot left. So index 1, so we are at this cell, right? What is a left child? Left child is this one. But what is the index of this vertex? 2. So the index 1 vertex is pointing to its left child, which is at index 2, right? So the left value is 2. Okay. Now index 2. Index 2 is pointing to its left child. Its left child is, sorry. Yeah. Index 2 cell is pointing to its left child. Its left child index is 4. Right. So index 2's left child is 4. Okay. What about index 3? Right. We'll go on filling in the same order. Index 3. Index 3's left child is this one. And its index is 6. Right. So the third index, the left child is 6. Right. And correspondingly, you can keep checking. Third index, the key value is 5. Okay. Keep checking that we are not making a mistake. Okay. It's 6. So the left index is 6. Fourth one, pointing to its left child, index 8. Right? Fourth has index 8. Fifth one is this. Fifth left child index is, left child is this. Its index is 10. Okay. Whereas the sixth one? Sixth one is this. Sixth left child is this one. If you just notice carefully, its index is 12. So the sixth one has index 12. Seventh is this one. Seventh one's left child is this, and its index is 14. So we have 14. And now, if you notice, 8, 9, 10, 11, 12, 13, 14, 15. These are the bottommost elements. These are called leaves of the graph, because they don't have anything going down further. The bottommost elements don't have any children. So the left child pointer has to be empty for each of those, right? So now, henceforth, it's 8th one empty, 9th one empty, 10th one empty, 11th empty, 12th empty, and so on. Okay. From then on, all of these are empty. Is that okay? That's it. Now, similarly, you can do for the right child. So right child, now I'm going to keep filling it. Correspondingly, look at the tree and check that I'm not making any mistake. Okay. Okay. So let's do that. First one's right child is 3. The index is 3. Second one's right child index is 5. Third one's right child index is 7. Fourth right child index is 9. Fifth right child index is 11. Sixth right child index is 13. Spacing. I'm maintaining a spacing so that it becomes easy for you to read. Okay. So where were we? Sixth index right child is 13. Seventh index right child is 15. After that, 8, 9, 10, 11, 12, 13, 14, 15 have no right child either. They have no left child, they have no right child. So it's the same thing. Okay. Now let's look at parent. Parent is pointing upwards. So I'll just show you quickly what is a parent. So for instance, if you take index 5, its parent is the one above it, index 2, right? Index 18, its parent is index 12, the value is 18. This one, index 12, its parent is the vertex with index 6. Okay. What about index 1? Index 1 has no parent, so its parent is empty. Is that all right? So now I'll keep checking. I'll just go on filling this, filling the parents also. So index 1, parent is empty. Index 2, parent is 1. Index 3, parent is 1. Right? There are parents are going to appear twice because there are two children. Two children will point to the same parent. Right? So 1 will appear twice, 2 will appear twice, 3 will appear twice, and so on. So index 3 parent is 1, index 4 parent is 2, index 5 parent is 2, index 6 parent is 3, index 7 parent is 3, index 8 parent is 4, index 9 parent is 4, again index 10 and 11 parent is 5, index 12 and 13 parent is 6, index 14 and 15 parent is 7. Okay, so there is only one empty parent pointed, only for the top one, if you see here, right? Because this one's parent is empty. But everyone else has a parent. There are two children pointing to the same parent everywhere. So the parents will appear twice in this case, each of the parents. Is that okay? So this is the linked list representation of a binary tree, doubly linked list representation. Okay, I have done both. Okay. Now, if I ask you singly linked list representation without pointing only to children and not pointing to parents, only to children and not pointing to parents, then it will only be this much. If you see parent pointers, the upward pointers will not be there. Okay. But if I tell you only parent pointers but not the children, which is upward, you only show the upward. Downward ones are not going to be there. So the children will not be there, only the parents will be there. Okay, that is also fine. this is how it will look. Okay, so we have covered both in this case. So okay, so now let me quickly write down this thing. It's easy to check. So now you have to check this, okay, which is binary tree as a LLW. That is what this is. Binary tree as LL, but point to children. Okay, what will that look like? This much. Okay, then binary tree as a LL point to parent. You understand? Pointing to children or pointing to parent only means it is singly linked. Okay, singly linked. Sorry, not this one. Only to parents, so only this much. Is that okay? So just in case you want to see the code a little larger, this is what it is. Is that all right? So for the moment, I will stop here and I'll let you go through this and think about this for a while. Okay, so that is the end of this video. Next time we will do a little bit more with these linked lists. Look at some more examples and some more programs, so to speak. All right, so thank you very much. Yeah.